Is the screen visible, students?
Yes, sir.
Screen is visible. Okay, all right. So we're discussing about the potential, topic on potential. Next is potential due to line charge. Consider the line charge. This is the line charge with the line charge density Royal Coulomb per meter. Line charge density is nothing but charge per unit length, Royal Coulomb per meter. Then we are considering differential length dl dash on this line charge. On this line, we are considering a differential length dl dash. This dl dash is at a distance of r dash from the origin. Dl dash is at a distance of r dash from the origin. We are interested in finding the potential at point A due to the differential charge dq present at dl dash. If the differential charge, small amount of charge dq is present at dl dash, what is the potential at point A? That we have to find out. Okay. Consider line charge having density Royal Coulomb per meter. The differential length dl dash is a distance of r dash from origin. Hence, the differential charge dq on the length dl dash is given by, you know the equation for dq. dq is given by Royal r dash dl dash. Royal into r dash into dl dash. Actually, dq is just equal to Royal into dl or Royal into dl dash, because the equation of line charge density is charge per unit length. dq by dl is equal to Royal, right? But here it is Royal into r dash. It is Royal into r dash because in the previous equations that we had obtained, right, there we had not considered the origin. With respect to origin, it was just from the line charge. Okay, we had not considered from the origin, but here as we are considering from the origin, the line charge density will be modified to Royal into r dash. It will not be just Royal here, whatever is the line charge, it will be Royal multiplied by this distance r dash. That will be the line charge density with respect to the origin. With respect to the origin. Okay, in the previous topics whatever we have studied, we have not considered with respect to origin. As we are considering here with respect to origin, therefore the line charge density will be Royal into r dash. As the line charge density is modified to Royal into r dash, therefore dq will be equal to line charge into dl or line charge into dl dash, because we know that line charge density is charge per unit length, that is Royal into r dash is dq by dl, or dq is equal to Royal into r dash into dl dash. Take it as first equation, where Royal into r dash is line charge density at r dash. Now the potential at A we have to find out. Then dVA, if we are supposed to find the potential at this point A, then dVA, that is small engine small voltage dVA at the point A, differential voltage, is given by the formula excuse, dq divided by 4 pi epsilon naught into r minus r dash. dq divided by 4 pi epsilon naught into r minus r dash. We know this formula for potential. V is given by q by 4 pi epsilon naught r. Correct? That is further equal to dq divided by 4 pi epsilon naught into capital R, where capital R is the distance, that is r minus r dash. It is a distance between the point A and the differential charge dq. The distance between point A and the differential charge dq at dl dash. That is the capital R. dVA is the differential potential at A. dVA is the differential potential at point A. If we want the total potential at point A, then we have to take the integral, line integral, okay, line integral over the length over which the entire charge is distributed. We have to take the line integral of the differential potential dVA to obtain the total potential VA at the point A, right? That is what we are taking at the next equation. dVA is the differential potential at point A. Hence, the potential VA, if we want, we have to integrate to get the total potential. Can be obtained by integrating dVA over the length where line integral or line charge is distributed. That is, VA is given by V of R. That is the line integral. We have to take the line integral because we are studying the potential due to line charge. Line integral of dq divided by 4 pi epsilon naught R from equation to whatever is we have written. That is VA is equal to V of R, that is line integral. This dq, we know that it is Royal r dash dl dash, rho l into r dash into dl dash. That is line integral rho l into r dash into dl dash divided by 4 pi epsilon naught r volts. This is the final equation for potential at point A due to the line charge. Potential at point A due to the line charge. Okay. I hope this derivation is clear for you all students. Yes. Derivation is clear. Potential due to line charge. Any difficulty here in this derivation?
Sir, clear,
Small
sir.
derivation. Clear. Okay. Next, similarly, as we have found out for the line charge, let us find out for the surface charge. It is almost similar. Okay. Consider the uniform surface. Consider the uniform surface.
Sir,
Whose,
excuse me, sir.
yes, please. Here, Hashkoda.
Sir, how that r minus r dash is equals to capital R, sir?
Yes, I'll tell that. Here, whenever you are finding the distance, okay, this distance between the point A at which you are finding the potential and the charge dq of the elemental charge. Okay, whenever you are taking the potential at point A, one is the origin. One is the origin. One we have origin here, and the another we have two charges here. Okay, this is our origin. We have one charge at A. We are supposed to find the potential at A due to the charge which is placed at the length dl dash. Okay, with respect to the origin, it is always with respect to the origin. Therefore, if we want this distance, because what is the formula here? Our formula is dV is equal to dq divided by 4 pi epsilon naught r. Okay, this is our formula for the potential, or V is equal to q by 4 pi epsilon naught r. Capital R is nothing but the distance between the point A and the differential charge dq, which is there on line dl dash, which is there on the line dl dash, right? So this distance is given by always, understood, no? Okay, this distance origin to A, my destination minus source. Destination is point A, source is dq, so r minus r dash. With respect to origin, we have to take always. That will give us the distance from point A to the differential charge dq, right? Okay. Potential due to surface charge. Let us consider the surface, right? Let us consider a surface whose charge density is rho s coulomb per meter square. Its charge density is rho s coulomb per meter square, as shown in this figure here. Then on this surface, we are considering small surface, differential surface ds dash. Ds dash is the small surface that we are considering at point P, where rho s is rho s into r dash. Because with respect to origin, we have to take, as we have found out here, for with respect to origin, it is rho s into r dash, rho l into r dash here for the line charge, correct? So if we take with respect to origin here for the surface charge also, it will be rho s into r dash instead of rho l into r dash. This is surface charge, and hence it will be rho s into r dash. Next, let us write the equation for
Excuse me, sir.
differential. Yes, please. Here,
Sir, please allow Kirti, sir.
okay, 1 minute. Prathamesh Kinekar, I am admitting. Kirti, she joined or what? Kirti? Just ask her to join. Kirti, okay. Kirti and Sagar, both are here. Okay, fine. Right. Next, the differential charge can be written as dq is equal to, as we wrote for line charge, dq is equal to rho s into r dash into ds dash. For line charge, what we have written, dq is equal to rho l into r dash into dl dash. So it is only rho l into dl or rho l into dl dash, that is dq. But here we are taking rho l into r dash because we have to take with respect to the origin. Hence it is modified to rho l into r dash. Here it is rho s into r dash for surface charge. That is dq is rho s into r dash into ds dash, where ds dash is charge per unit area, because it's a surface charge per unit area. That is dq by ds. Therefore, it is dq is equal to rho s r dash into ds dash. And dva, it is given by dq by 4 pi epsilon naught r. That is dq is rho s into r dash into ds dash divided by 4 pi epsilon naught r. Now r is again the same thing. It's the distance of this point A from the differential charge Q, which is present at ds dash. The distance from point A to the differential charge dq, which is present at ds dash, that gives the distance capital R. Total potential. Next, if you want to find total potential, then we have to integrate. Is it not? We have to integrate this dVA to get the total or the total potential. dVA over the given surface, that is VA is given by integration of dVA. Here, which integral we have to take? Single integral or double integral? It's a area. Which integral we have to take here? We have to take double integral. For line, it is single integral. It consists of two coordinates, no, x and y, or y and z, or x and z in Cartesian. Correct? We have to take two integrals for surface area or for the area. For line integral, it is single. For volume integral, it is triple integral because it has three coordinates, x, y, and z, three-dimensional. Yes. Therefore, we are integrating to get the total potential. VA is equal to surface integral rho s r dash ds dash divided by 4 pi epsilon naught r volts. This is the equation for the total potential at the point A. At this point A, the total potential due to surface charge is given by surface integral rho s r dash ds dash divided by 4 pi epsilon naught r volts. Okay. I hope this derivation is clear for you all students. Any difficulty here in this potential due to surface charge? This is clear. Potential due to surface charge. Any questions, any doubts here?
Understood, sir.
Okay, fine. Next is potential difference due to infinite line charge. Okay, we already found out the equation for electric field intensity due to infinite line charge. Is it not in our module 1? Electric field intensity due to infinite line charge. Here we are finding the potential due to infinite line charge or the potential difference due to the infinite line charge. Consider, it's your test question. Consider an infinite line charge along z-axis, having uniform line charge density rho L coulomb per meter. We are considering an infinite line charge along z-axis and its line charge density is rho L coulomb per meter. The point B, this is the point B, this is at a distance of RB. It is called as radial distance, right? Radial distance means if you are considering the cylindrical surface with this radius RB, then this radius RB will be perpendicular to the surface of the cylinder. It will be perpendicular to the surface of the cylindrical surface that you are considering here, right? And hence it is called as radial distance. Then suppose if you are considering a cylinder in cylindrical coordinate system, if you are considering a cylinder at point A, right, at point A, then this is the radius RA of that cylinder, and hence it is perpendicular to the surface of the cylinder and it is called as radial distance RA. Then E bar due to infinite line charge, we know this equation already, we have already derived in module 1. E bar due to infinite line charge along z-axis, E bar due to infinite line charge along z-axis is given by the equation. Can you tell me the equation, students? What is the equation for E bar due to infinite line charge? Electric field intensity due to infinite line charge. Yes, can you tell me the equation? E bar is given by, you will have to remember the equations. Every equation is important. So it is given by E bar is equal to 2L by, rho L by 2 pi epsilon naught r AR bar. Rho L by 2 pi epsilon naught r AR bar. Yes, please. Yes, please. Any doubts here, students? You want to ask anything, students?
No, sir.
Okay, right. E bar is equal to rho L by 2 pi epsilon naught r AR bar. This is the equation for the electric field intensity on z-axis. Okay, due to infinite line charge on the z-axis. Then DL bar, this equation we have already derived in module 1. I am taking from there. Okay. Then dl bar, it is just the radius vector into its unit vector, because here we are considering the cylindrical surfaces with respect to radius. The cylinder, if you are considering one cylinder at point A, okay, it is at a distance of RA. Its magnitude is taken in terms of radius. Correct? It is considered with respect to the radius RA. Similar, if you are taking another cylinder at point B, at a point B cylindrical surface, then that cylinder is considered with respect to the radius, radial distance RB. Okay, and hence as it is considered with respect to radial distances RA and RB, therefore there are no other coordinates, that is phi and z will be neglected. We are neglecting the phi and z coordinates because the cylinders that are considered here, they are measured or they are considered with respect to radial distance. They are considered with respect to the radial distance RA or RB. They are at a radial distance of RA. Another cylinder at B is at a radial distance of RB. Fine. And hence the dl bar will not be in terms of r, phi and z. Okay, it will be in terms of only dr and ar bar. That is a radius vector with its unit vector. That is dl bar is equal to dr ar bar. Dl bar will be dr ar bar in cylindrical system, that is in radial direction. Therefore VAB is nothing but, we have also gone through this equation in previous classes. That is potential A to B is given by minus integral B to A E bar dot dl bar. We have already come across this equation. Yes or no? VAB is minus integral B to A E bar dot dl bar. What is B, students? What is the distance of B? It is at RB. It is at RB. Distance of A is at RA. Yes, distance of A is at RA. So write it, minus integral RB to RA. E bar is known, rho L by 2 pi epsilon naught R AR bar. Then DL bar is DR AR bar. So it is dot of DR AR bar. Correct? That is minus integral RB to RA, rho L by 2 pi epsilon naught R. What is AR bar dot AR bar, students? It is 1. Yes or no? AR bar AR dot AR bar is 1. The unit vector dotted with itself is always 1, unity. Therefore, it will be simply minus integral RB to RA, rho L by 2 pi epsilon naught R dr. Yes, that is minus rho L by 2 pi epsilon naught is constant, take it outside, over the integral RB to RA 1 by R dr. What is the integral of 1 by R? Can you all tell me? Integral of 1 by R.
Log R, sir.
Log R or ln R? Is it not? Log R or ln R. If you are taking to the base 10, it will be log. If you are taking to the base E, Napier base, then it will be ln. Correct? Either you can take it as log or ln. So it is minus rho L by 2 pi epsilon naught ln R, then over the limits RB to RA. Okay, lower limit to upper limit. It is minus rho L by 2 pi epsilon naught ln RA minus ln RB. Upper limit is ln of RA minus lower limit ln RB. That is VAB will be equal to, this is minus here outside. So if I multiply this minus 1 inside, what I will get? Ln RB minus ln RA. Yes, rho L by 2 pi epsilon naught into ln RB minus ln RA. That is ln RB by RA. So I am writing it as VAB is equal to rho L by 2 pi epsilon naught ln of RB by RA volts. This is the value of potential difference VAB, or the value of potential. Okay, value of potential between points A to point B due to the infinite line charge lying on the z-axis. Is it clear here, students? How to find the potential difference equation due to infinite line charge? Due to infinite line charge, we have derived the equation for the potential difference between the points A to B, and it is given by VAB is equal to rho L by 2 epsilon naught ln RB by RA volts. Is this derivation clear here, students? Any difficulty here in this derivation? Anything not understood? Any problem in understanding? You can tell.
Understood, sir.
Fine. Okay, we'll proceed. Next is the topic on potential gradient. Okay, let us try to understand what is this potential gradient. Let us consider an electric field E bar due to a positive charge placed at the origin of a sphere. It's a sphere, right? And at the origin of the sphere, at the center of the sphere, a positive charge is placed, and we are considering the electric field intensity E bar due to this positive charge placed at the center of the sphere, at the origin of the sphere. Then we can write the equation for potential in terms of electric field intensity and the differential length as V is equal to minus integral E bar dot dl bar. V is equal to minus integral E bar dot dl bar, that is Q by 4 pi epsilon naught R. Okay, we are familiar with these equations, correct? We have come across many times till now this equation. V is equal to minus integral E bar dot dl bar, that is equal to Q by 4 pi epsilon naught R. The potential, this potential V, it decreases as this distance R increases. Why? As this distance R increases, why the potential V should decrease? Yes, any reason? Any reason here?
Sir, Ohm's
Can
law,
you?
sir. Ohm's law.
Ohm's law? No, no, no. That is resistance. This is a distance. Don't get mixed up with those. Here, what I am telling is V is equal to Q by 4 pi epsilon naught R. That is, R is distance here. It is not the resistance. Please note here.
Sir, inversely
R is
proportional, sir.
Yes, you are right. It is inversely proportional. Voltage is inversely proportional to the distance R. Fine. That is why as R increases, as distance increases, potential should decrease. As the distance decreases, potential should increase. That means there is a inverse relation between the potential and the distance. The line integral of E bar, if we take the line integral of this E bar over the length dl bar, then it gives the potential difference between those 2 points. Let us say I am taking the line integral minus line integral of a to b E bar dot dl bar, minus line integral a to b E bar dot dl bar. Okay, then what it will give us? It will give us the potential difference between the 2 points A to B, because this is equal to V, that is our LHS. Is it not? LHS is V. V is equal to minus integral E bar dot dl bar. If I take the integration minus integration A to B E bar dot dl bar, that is equal to our potential, and hence as we are taking between the points A to B, it will give us the potential difference between the 2 points A to B. Let us consider elemental length delta L here. Elemental length, instead of dl bar, if we consider it as delta L, look at this figure graph. This is a graph of the potential versus distance. As the distance increases, R increases, potential decreases according to this equation. V is equal to Q by 4 pi epsilon naught R. And as R decreases, potential increases. Yes, this is our length that we are considering, delta L, small incremental length, over which the potential difference is delta V. A to B. A to B potential difference it is, because it is a difference in potential between the points A to B, and hence it is delta V we are considering. The differential length between A to B, that is considered as delta L. So I can write the equation as V A to B, that is potential difference, is equal to delta V, that is, if I consider small length, then I will write it as minus E bar dot delta L, minus E bar dot delta L bar. This integration symbol will come only when I want the VAB or delta V of the entire line or the entire surface or the entire volume. Yes, now this is a small length I am considering, small incremental length, hence the integration symbol will not come here. That is why I am writing here VAB is equal to delta V, that is minus E bar dot delta L bar. The same equation what we have written here, the first equation. VAB is equal to delta V, that is equal to minus E bar dot delta L bar. Instead of DL bar, I am taking it as delta L bar. That is the only difference. The rate of change of potential, that is here as delta V changes with respect to delta L, this is called as potential gradient. What is potential gradient? The rate of change of potential, that is delta V, with respect to the distance delta L, is called as potential gradient. And mathematically we write it as dV by dl. That is, this is dV, then this is dl, right? dV by dl, that is equal to limit as delta V by delta L as delta L tends to 0. It is the same equation that we have written here. That is delta V by delta L, limit as delta L tends to 0. Delta V, that is our potential, divided by distance delta L as delta L tends to 0. Okay, it is our potential gradient. Now you all can ask me why we are taking the limit as delta L tends to 0. We are taking the limit as delta L tends to 0 because we are finding at a point. It's a small incremental length, right? The small incremental length delta L, it is a some point. Yes or no? Hence we are taking it as limit as delta L tends to 0. That is our next point. Potential gradient is the slope of the graph. It is nothing but slope, correct? Delta V by delta L, that gives the slope of this curve, which is a graph of potential versus distance. Graph of potential versus distance. Yes. Potential gradient is the slope of the graph of potential against distance at a point where elementary length is considered. Where at a point, it is at a point, note that. It's at a point where elementary length is considered. Hence, we take limit of delta V by delta L as delta L tends to 0. Tends to 0 means it is at a single point, at a particular point. That gives the formula for the potential gradient. Okay. Is this understood, students? What is potential gradient? It's an important topic from examination point of view. Many times they have asked this in examination. Potential gradient. They'll ask to explain the potential gradient. And next one is one more important derivation, okay, which is they are asking repeatedly in the examination.
Sir,
Any
can you explain
difficulty
once
here?
again, sir?
Okay, I'll explain that. The concept is very simple. See here, first thing is we have to know this formula. We know this formula already, is it not? B is equal to minus integral E bar dot dl bar, that is equal to Q by 4 pi epsilon naught R. This formula also we know, that is V is equal to minus integral E bar dot dl bar, and just now we have used the equation V is equal to Q by 4 pi epsilon naught R. Okay, that means I can equate V is equal to minus integral E bar dot dl bar, that is also equal to Q by 4 pi epsilon naught R. Yes, so these equations we are knowing, we are very much familiar with these equations. Now we are establishing the relation between the potential V and the distance R, right? We are finding the relation between the potential V and this distance. Small r is there, no, or the capital R, whatever is the distance between these two, we are finding the relation. Now the relation between these two is that we have to look into this graph if we want to know the relation. We already come to know analytically, we will come to know that both are inversely proportional. Potential is inversely proportional to distance. If distance increases, potential decreases. If distance decreases, potential increases. Correct? They are inversely proportional to each other. Now how to draw it mathematically, or how to explain it graphically? This is mathematically, analytically. If we want to explain it graphically, then we have to draw the graph of potential, that is voltage, versus distance, that is small r or capital R. Then as we increase the distance, the potential is decreasing. As we decrease the distance, the potential is increasing. It's a curve, right? As the R increases, V decreases. As R decreases, V increases. Is it not? Then I'm considering 2 points here. One point is A on this curve, another point as B. Then take the intercepts. Take the intercepts. You know how to take the intercepts mathematically, right? So this is how we are taking the intercept. This is on y-axis. This on y-axis, that is our v-axis here. Then the intercepts from A to B on x-axis, that is on r-axis here in our particular topic what we are studying here. So this distance from A to B, it is delta V, change in potential. At A there is some potential, at B there is some potential. The difference between the potential at point A and point B is delta V. Delta V. Yes. Similarly, at A there is some length and B there is some length. If we take the difference between those two lengths, then we'll get a small length, incremental length. Okay, that is our delta L. Delta L. Fine. Now, if we consider this, then I can write the one more equation here. VAB is equal to delta V. VAB is equal to delta V, that is A to B. Voltage between A to B is delta V, that is minus E bar dot delta L bar. minus E bar, that is the same what we wrote in equation 1. It is E bar dot dl bar. So it is minus E bar dot delta L bar. DL bar is same as delta L bar. Both are one and the same. Now why I'm not taking the integration here? I'm not taking the integration because it is for small length. It's for small length. It is, we are taking a very small difference here between A to B, right, for a point charge, and hence we are not integrating. If you want for the entire length of this curve, then we have to integrate. Yes, then we have to integrate between the points A to B or whatever are the points here on the curve. We have to integrate from that point to destination point to source point to destination point. Is it not? So we got this equation here. This is our equation. Then later the equation, what is potential gradient? That is the definition of potential gradient. The rate of change of potential, that is dV, with respect to the distance, that is dV by dl. Okay, dV by dl. This gives the potential gradient. Okay, that is we write limit of delta V by delta L as delta L tends to 0. We are taking the ratio here, dV by dl, that is ratio of the potential to the distance. Yes, so delta L tends to 0 because we are finding the potential gradient at the particular point, single point. Okay, that is why we have to take the limit as delta L tends to 0. Length is tending to 0 means if the length becomes 0, what it indicates? It is a single point. Correct, the single point. Suppose if the volume, if you are making the delta V volume 0, we have studied this in divergence equation. Delta V, if it tends to 0, what you are getting? You are getting a single point. The volume shrinks to 0. Correct. Similarly, if there is a line, if you are making the line limit as delta L tends to 0, if the line tends to 0, what you are getting? Finally, you are getting a single point. Yes, so it is a potential gradient at a particular point. That is, potential gradient is a slope of the graph. It is the slope of this graph. Is it not? Because it is delta V by delta L, y intercept divided by x intercept. What is the slope, students? Slope is equal to y by x mathematically. Yes, this is our y axis, this is our x axis. Slope is given by y by x, that is delta V by delta L against distance at a point where elementary length is considered. I hope now it is clear here. Yes,
Yes, sir. Understood, sir.
good. Okay, let's move on to the next topic, that is our relation between E bar and V. Very important relationship. This is asked many times in examination. Okay, let us consider the curved magnetic flux lines here, curved field. It's a curved field. Okay, that is, consider E bar due to a particular charge distribution in space. We are considering the electric field intensity E bar due to this charge distribution. It's a distribution of the charge. It is distributed like this. Okay, it's a curve, right? Curve distribution. The electric field E bar, it is making an angle theta with respect to the differential length delta L. We are considering the differential length delta L. This electric field intensity E bar makes an angle theta with the differential length delta L at a point P. Fine. The electric field E bar and the potential V is changing from point to point in space. Of course, it's a curved surface. Hence, E bar and V, electric field intensity and the potential, will change from point to point in the space. Consider a vector incremental length delta L, which makes an angle theta with respect to the direction of E bar. Delta L makes an angle theta with respect to the direction of E bar. To find the potential, we use delta V is equal to, that is incremental potential, delta V is equal to minus E bar dot delta L bar. The same equation what we have got here. Let us go back. Here it is. Delta V is equal to potential gradient definition. Delta V is equal to minus E bar dot delta L bar. Write the same equation. Delta V is equal to minus E bar dot delta L bar. Here delta L bar, that is the incremental length. If you want to represent the incremental length, we have to use the magnitude along with the direction. Magnitude is given by delta L and the direction is given by the unit vector AL bar. Correct? Unit vector AL bar gives the direction, delta L gives the magnitude. Then AL bar is a unit vector in the direction of delta L bar. Then we can write E bar dot delta L bar. E bar dot delta L bar. E bar is the vector, so its magnitude is EL and its unit vector is AL. Here, look at this equation, this diagram. So its magnitude is E bar, and in the direction of E bar, the unit vector, if it is AL, so it is E bar AL bar. E bar AL bar. E bar is the magnitude and AL bar is the direction of the electric field intensity E bar. E bar is magnitude and its direction is given by the unit vector AL bar. Yes. It is EL AL bar. Dot of delta L bar is delta L into AL bar. Delta L AL bar. Now AL bar dot AL bar will be 1. AL bar dot AL bar, unit vector dotted with itself is 1. If you are taking the dot product of the unit vector with the same unit vector, then its dot product will be always equal to 1. Yes, that is E bar dot delta L bar will be EL delta L, EL delta L. That is delta V. What is our delta V here from equation 1? Minus E bar dot delta L bar, that is delta V. Yes, so here we are having E bar dot delta L bar, that is equal to LHS, that is minus delta V is equal to EL delta L, or delta V will be equal to minus EL delta L. How we are getting this? E bar dot delta L bar is equal to EL delta L we got. Is it not? Now here if we look at the equation 1, it is having E bar dot delta L, E bar dot delta L bar. Here also LHS there is E bar dot delta L bar. Now this RHS is equal to LHS, that is delta V. Yes, so I am writing delta V is equal to, there is minus delta V is equal to EL delta L, or delta V is equal to minus EL delta L. In other words, dot product can be expressed in terms of cos theta. We know what is dot product. E bar dot delta L bar, it is a magnitude of E into magnitude of delta L into cosine of angle theta. E bar dot delta L bar is equal to magnitude of E into magnitude of delta L into cosine of angle theta between E bar and delta L bar. That is delta V. What is our previous equation? Delta V is equal to minus EL delta L. It is delta V is equal to, this is a EL delta L, correct? It is a E bar dot delta L bar. It's a dot product. Hence I can write it as dot product E bar dot delta L bar. This is dot product here. Okay. So this I can write it as E bar dot delta L bar sine of theta, because here we are getting minus sign. Is it not? Minus. So I can write it as delta V is equal to minus of magnitude of E bar to magnitude of delta L bar into cosine of angle theta between E bar and delta L bar. The same equation I have written here. Delta V is equal to minus E bar into magnitude of delta L into cosine of angle theta between E bar and delta L bar. So delta V by delta L, if I take the ratio here, delta V by delta L, this will give me minus E cos theta. Rearrange the terms. We get delta V by delta L is equal to minus E cos theta. Next, find delta V at a point. What I told previously, students, if you want to find the delta V at a point, we have to take the limit as delta L tends to 0. Limit as delta L tends to 0. Hence, limit as delta V by delta L as delta L tends to 0, that will give me minus E cos theta. That is, but we know delta V by delta L as limit delta L tends to 0 is dV by dl. From where we got this equation? Yes, students. From where we got this equation?
Potential gradient, sir.
Limit. Yes, please.
Sir, potential gradient.
Potential gradient. Good. So here in the previous one, we have got the potential gradient. In the previous topic, potential gradient, we have obtained the equation dV by dVL is equal to limit as delta V by delta L as delta L tends to 0. That is our potential gradient. The same equation for potential gradient. Is limit as delta V delta L tends to 0, delta V by delta L is equal to dV by dl, that is potential gradient. Hence I can write dV by dl is equal to minus E cos theta, because this LHS is equal to dV by dl. This LHS is dV by dl. Hence, therefore, dV by dl is equal to minus E cos theta. At a point P where delta L is considered, E bar has a fixed value while delta is also a constant. If you are considering point P, delta L is constant, is it not? It does not change. It's a point. Is there any change in the point? No, it is fixed. And E bar is also fixed because it's a point. If the length changes, then only E bar will change. As the length is constant, delta L is constant, E bar is also constant. That is, potential gradient dV by dl can be maximum when cos theta is -1. Look back at the equation. dV by dl is minus E cos theta. When will dV by dl be maximum? When cos theta is -1. When cos theta will be -1, for what angle? How much is cos 180? Cos 180 is how
-1, sir.
much? -1. You are right. -1. So it is minus E into -1. That will be plus E. Therefore, dV by dl will be maximum. So cos theta, that is cosine of 180 degree, it will be -1, for which we are getting dV by dl as maximum. Cos theta is -1 at theta is equal to plus 180 degree. This indicates that delta L must be in the opposite direction to that of E bar. Look at the equation. dV by dl is equal to minus E cos theta. That is, when length dl, if we take the relation between dl and E, when E is positive, dl is negative, because dl is at the LHS side. dl is on the LHS side, E is on the RHS. If E is positive, dl will be negative. If E is a negative, dl will be negative to negative of negative. It is positive. dl will be positive. It indicates that dl and E, they are 180 degree out of phase with respect to each other. That means dl and E, they are 180 degree out of phase with respect to each other. This indicates that delta L must be in the opposite direction to that of E bar. So we have obtained the equation dV by dl maximum is equal to E. dV by dl maximum is equal to E, because cos theta is -1. -1 into -1 is plus. Therefore, dV by dl maximum is plus E. This equation shows that the dV by dl, that is rate of change of potential with respect to distance, it is called potential gradient. Potential gradient equation, it gives the equation for the electric field intensity. This is one conclusion, and we can draw from this equation. Another point that we can draw from this equation is that the rate of change of potential with respect to distance, that is potential gradient, maximum value is obtained only if delta L is opposite in direction to that of E bar. If delta L is dl is opposite to that of E bar, then only we are getting the maximum value, that is theta will be 180 degree and cos theta will be -1, and hence we will get dV by dl maximum, that is plus E. These are the 2 points that we can understand from this equation. dV by dl maximum is equal to E. The first point is maximum value of the potential gradient is the magnitude of the electric field intensity E bar. Second point, maximum value of change of potential with distance. It is called potential gradient is possible, that is maximum value of potential gradient is possible only when the direction of increment in distance, that is dl, is opposite to the direction of E bar. Fine. Now actually, if you want to write the vector of E bar, how to write it? Minus dV by dl, we have to consider with sign, because we are writing the vector, it is magnitude with respect to direction. Therefore, we are considering the minus dV by dl. dV by dl is equal to minus E at a unit vector along with the unit vector. That is minus dV by dl max with the unit vector En bar. The vector, we have to write both the magnitude as well as the direction. Direction is always given by the unit vector. Yes or no? As E bar and potential gradient are in opposite direction, E bar and potential gradient, that is dV by dl, they are in opposite direction. The equation has the negative sign. We know the maximum value of rate of change of potential with distance, that is dV by dl, is called gradient of V. This maximum value of rate of change of potential with respect to distance, that is dl, dV by dl, is called gradient of V. Gradient of V. The mathematical operation on V, the mathematical operation on this potential V, by which minus E bar is obtained or E bar is obtained, is called gradient, and it is given by gradient of V is equal to gradient of V, that is del V. Okay. Note the difference between del V and del dot V. Okay, we are solving one example next, and you'll understand the difference between del V and del dot V. Okay, del V is called as gradient of V. If you're taking del dot V, it is called divergence of V. Okay, we'll solve an example, then you'll understand there. Okay, del V is, if you are not using the dot in between, it is called as gradient of V. If you are using a dot in between, del dot V, it is called divergence of V. Okay, please be very much clear about this point between gradient of V and divergence of V. Therefore, del V is given by, it is gradient of V, that is minus E bar. Gradient is nothing but dV by dl. dV by dl. That is del V is equal to gradient of V, that is dV by dl, that is minus E bar. Minus E bar, volt per meter. And hence, finally, I can write the equation as E bar is equal to, this E bar is equal to minus del V. E bar is equal to minus del V, that is equal to minus gradient of V. Minus gradient of V. This is the final equation which gives the relationship between electric field intensity and the potential. It is giving the relationship between the electric field intensity E bar and the potential. Very important relation. The relation is electric field intensity is the negative gradient of the electric potential. How to define it? Electric field intensity E bar is negative gradient minus del of the electric field potential. This is the relation. Here V is a scalar quantity. V is scalar quantity, but if you take E bar, gradient of V, it will be vector quantity. It will be clear for you when we'll be solving the next example. E bar is minus gradient of V or minus del V. V is scalar quantity, but E bar is vector quantity because it is gradient of the scalar quantity. Gradient of the scalar quantity is always a vector quantity. Remember, gradient of a scalar quantity is always a vector quantity. Any difficulty in this derivation, students? Practice all these derivations, numericals, right? They have been asked in examination. In examination, they will twist certain values and they may ask, they may give the same example or they may slightly change the values. Okay, the similar example, they may change the values and they may ask you all for in the examination. Okay. It's a completely, say, visualization subject where we are supposed to visualize, we have to imagine, right? It consists of a number of numericals, derivations. Okay. Any difficulty in this derivation, students? Any difficulty in this derivation? I hope you all understood here. If you are
Understood,
having any
sir.
questions, any doubts, you can ask. Any questions, any doubts here? Yes.
No, sir. No doubts.
Okay. Ankita, any doubts?
No, sir.
Understood everything, today's derivations?
Yes, sir.
Okay. Harshgoda, understood?
Yes, sir. Understood, sir.
Okay. Mohammed Mazhar. Mohammed. Samir Ahmad Khaji.
Yes,
Samir
sir.
Ahmad Khaji. Today's derivations clear, Samir Ahmad?
Yes, sir.
Concepts? Fine. Rohan Chandekar. Rohan,
Yes, sir.
is the derivations clear, Rohan? Did
Yes,
you
sir.
understand here?
Yes, sir.
Any difficulty, any problem in understanding?
That's understood.
Understood. Good. Pallavi Dharegowda. Pallavi,
Yes, sir.
was
Yes, sir.
it clear today's discussion, Pallavi?
Yes, sir.
Understood everything? All topics what we discussed in
Yes, sir.
today's
I
class.
understand.
Fine.
Yes, sir.
Good. Shweta Paushe. Shweta.
Yes, sir.
Did you understand the today's concepts, points,
Yes, sir.
derivations, everything?
Yes, sir.
Is there any question, any doubt in today's class?
No, sir.
Okay, fine. Shraddha Hunshal. Shraddha.
Yes, sir.
Was it understood, Shraddha? Today's class topics.
Yes, sir. Understood.
Good. Okay. Okay, students. Then we'll continue in the next class. Next class we'll be solving one example. Okay, we'll be solving an example on this derivation. Okay, one or two examples, and then we'll proceed to the next part. Okay. In today's class, we have discussed the topics on, that is, we started with the potential due to line charge, then potential due to surface charge, potential due to line charge. This is the equation that we have got. Just note this equation. Then potential due to surface charge, it is similar to potential due to line charge. Slight, instead of dl dash, we'll get ds dash. That is the only change in the equation. Rest of the equation remains the same. And there we get line integral. Here it is double integral or surface integral. These are the differences. Then potential difference due to infinite line charge. The equation that we obtained is VAB is equal to rho L by 2 pi epsilon naught ln RB by RA volts. Potential gradient, we defined what is potential gradient, and then we have explained it graphically considering this graph. Then the final equation for potential gradient is dV by dL is equal to limit of delta V by delta L as delta L tends to 0. That is our potential gradient. Then later we discussed the relation between E bar and V, where we derived an important relation between these two. And the final equation that we got is E bar is equal to minus del V. That is, electric field intensity is the negative gradient of the electric field potential. Okay. So we'll stop here. In the next class, I'll be continuing with the further topics. Okay. Thank you, students. Shraddha, I will give your attendance. Okay.